Good afternoon and welcome to our latest faculty. My name is Sarah Graham and I am delighted to be joined by my colleague today, Adal. Together we are going to talk about digital twins and the opportunities they present for the built environment in the context of sustainable design and operation. We will set the scene a bit by looking briefly at the advancement of technology in construction. And we'll do a bit of an overview on the emerging reality around the impact of climate change. The bulk of the session will be taken up with explaining the challenges and opportunities presented by city-scale modelling with some real-world examples. There will be lots of references for the audience to use as a jumping-off point to go off and do your own research, and we will have time for questions at the end. But first, we're going to launch the first poll of the session.
Okay guys, right, so we're just going to do a quick poll to get started, just to find out a little bit about who's on the line, who's currently using our products, if anyone's trialing or thinking about getting started. So we'll just give you a couple of, a minute or so just to respond to that. Okay, brilliant. Looks like most of you have answered that. We are actually about 50-50 are current users of our products and about 50% not. So I'm just going to close that now and pass back to Sarah.
By the way of setting the scene, I just want to really look at the phenomenon of Industry 4.0. In essence, Industry 4.0 describes the trend towards automation and data exchange in manufacturing technologies and process, including cyber physical systems, the Internet of Things, cloud computing and artificial intelligence. The term itself has been kicking around for some time, originating in Germany, but in recent times we've started to see quite a bit of crossover of the concepts into the built environment domain. We have lots of good statistics and examples around regarding the uptake of new technologies across the construction sector. I just want to highlight a few facts from this slide. So on the top right, of those surveyed, we can see that the majority of people agreed that digitisation of construction will improve productivity and delivery, assist in tackling sustainability, and help to improve health and safety. If we look at the bottom left of the slide, we can see the rates of adoption of different technology elements of Industry 4.0. So BIM is at the higher end, with VR and smart sensors somewhere in the middle, and AI and robotics at the lower end. If we look at the stacked chart in the middle of the slide, we can see that the majority of firms are still at the very early stages of their transformation to digitisation. So, digital twins bring together the different technology elements mentioned and effectively provide a virtual representation of the components and dynamics of a real object. Now that's an important point which we will be reiterating throughout this presentation. Digital twins are characterised by their connection between the real and the virtual, and by the ability to homogenise data. And I'll illustrate these in the practical examples later on. The manufacturing and automotive industries have successfully implemented digital twins for some time now to improve productivity and enhance customer satisfaction. Tesla creates a digital twin for every electric vehicle they manufacture, with all data flowing back to the manufacturing plant. So performance of any car can be tracked remotely, including things like downloading software to fix a rattling door, for example. In construction, digital twins are currently being used to address issues of risk around cost and programme overruns. Before the project starts on site, any problems can be sort of highlighted and resolved and potentially avoided once work has begun on site. In this slide we also see an example of predictive maintenance highlighted. So where it says notify the owner to replace the crankshaft bearing in 3 months, thus the connection between the real and the virtual is established and helps to understand when components will fail or to diagnose problems. So if we map some of those capabilities to design and construction and operation of buildings, one of the largest opportunities for the built environment is to optimise urban sustainability by creating a virtual replica of any city or community. and operators from there can develop different strategies to deal with people and traffic movement as well as energy, water and waste management. In the UK, the Centre for Digital Built Britain set out the benefits of an ecosystem of digital twins, a national digital twin, to the tune of £7 billion per year across UK infrastructure sectors, which is equivalent to 25% of total spend, so not an insignificant figure. In their Gemini Principles document, published last year, they state that digital modelling of the physical world is already sophisticated and is becoming ubiquitous. Digital twins enable better use, operation, maintenance, planning and delivery of assets, systems and services. So CDBB uses BIM Level 2 as a starting point for understanding what information is required to operate a facility and for structuring the data in such a way that it can be mapped across different platforms. But this has always been a waypoint on the journey to digitisation of construction, and we're still very much on that journey. Other examples of digital twins include Singapore. Virtual Singapore, created by the National Research Foundation, is described as a 3D semantic model enabling town planners to test solutions at low risk, in which the meaning of data can be related to the real world. So again, this connection. Apart from typical map data and land data, the platform also incorporates other real-time dynamics, as well as information about demographics, climate, traffic, making it a tool that offers enormous potential and which can be used in many different ways. So, alongside the rapid advancement of technology in construction, we have also seen an upsurge in opinion and activity around climate change in recent times. Politicians are starting to realise, given the recent groundswell of opinion with Extinction Rebellion and Greta Thunberg gaining huge amounts of support from around the world, that people want change. Amongst Generation X, there's a desire to take some responsibility for the legacy we pass on to our children and grandchildren. Generation Y are very switched on when it comes to technology and environmental impacts. They're the ones getting mortgages and will be looking for properties to live and work in that align with their environmental, social and economic values. But thus far, as we know, efforts have been slow and left wanting with respect to the magnitude of change required to limit global warming and associated impacts. We know that to meet the Paris goals by 2050, carbon emissions from energy and industry, which are still on the rise, will have to fall by 50% per decade. Emissions from land use will have to fall to zero, and we will need technologies to extract annually twice as much carbon from the atmosphere as the entire planet's plants currently do. Even if global decarbonisation is realised in 50 or 60 years' time through emission reduction and carbon capture, the world will still have warmed by perhaps 2 to 4 degrees with devastating effect. If fossil fuels peak in the next few years, as anticipated, the carbon dioxide in the atmosphere will continue to rise. Climate change will not have been stopped. A recent Mori poll showed that 85% of British adults are concerned over climate change, which is up almost 20% since 2015. 73% consider that we are already starting to feel the effects of climate change with the increase, for example, in extreme weather events. Fortunately, there is some hope in the growth of green technologies. Jeremy Grantham, an investor and author of Race of Our Lives, points out that the availability of affordable green energy will not be our downfall. Encouragingly, Grantham highlights the fact that the cost of wind and solar energy has fallen below that of coal, so it is the smart choice. Okay, it's poll 3.
Okay guys, so we just wanted to have a little look at what you think some of the barriers are that could prevent the use of digital twin technology in your organisation. And I'll quickly share the results just so people can see those there. So as you can see, the lack of skills and training and that access to data were coming up on top, followed pretty much equally by the lack of relevant technology, it being too expensive, and lack of demand in the industry.
Cities around the world have signed up to the Paris Accord, and many more have set out their plans to achieve zero carbon by 2050. But to make those commitments a reality, a real reduction in urban emissions requires increased focus on transforming energy use in buildings and transport, as well as a shift from fossil fuels to renewables, holistic approach to decarbonisation of city operations, infrastructure and services. Smart energy communities or zero carbon districts or positive energy blocks are among the labels used to identify district and community level schemes. Other environments with similar bounded characteristics include islands, university campuses, airports, and large real estate developments. Such projects represent an important upward scaling of climate action from individual sectors, for example, building energy efficiency and renewables as sort of siloed sectors, to a more holistic view that can encompass integrated energy systems and broader behavioural and social changes. Cities will become clusters of smart energy communities that can exploit the benefits of new energy systems. To realise the potential of community-scale projects with the complexities of integration of data across different sectors, planners, designers, managers and users require robust tools. Digital twin platforms can provide the complex modelling, analytics and simulation capabilities needed to support diverse stakeholder groups. The path to the decentralised, decarbonised and digitalised energy landscape begins with this transition to a low-carbon energy system. The next step is to fully integrate renewables. Then we go from there to implementing storage solutions to maintain flexibility, reliability and performance, using data analytics to anticipate demand and empower users, and finally, aggregation of distributed domestic and commercial energy sources into virtual power plants. With these challenges come opportunities. So in this section, we'll delve a bit deeper into the work that we've been doing to facilitate decision making on large-scale, multidimensional energy and sustainability projects. Our digital twin capabilities can help citizens, campuses, cities and communities understand the interdependencies across building optimisation, grid management and mobility planning, and can enable users to look at the options they have available to drive a transformation in energy consumption and the impact this will have on different communities. The ICL can address the design and operational performance of one or many buildings and associated networks. Using the ICL, we can homogenise data from any source in any format. Where real-time data exists for existing buildings and networks, we can pull that into the models, again, affecting this connection between the real and the virtual. Where no data exists, for example, where the buildings are planned but not yet constructed, we can use our simulation tools to complete the picture, understand the impacts of these new buildings and networks. We can set policy around that, for example, zero carbon for all new buildings. We can go beyond energy to the wider sustainability and urban metrics, including land use, population density, walkability, proximity of amenities, transport, water, etc. In individual buildings, if we think about the data that is typically available, even in older buildings, we usually will have meters on incoming gas, electricity and water. In newer buildings, we might have some sub-metering, some sensors for temperature, lighting, indoor air quality. The challenge really is building owners and managers are unsure what to do with the data. I mean, that in the last poll, we saw that getting access to data was one of the major sort of obstacles. And more importantly, don't have an insight into what that data can do for them. With our tools, we pull all the available data, time series data, whether it's BMS, meter data, sensor data, into a single platform, whether for one or many buildings, networks and or components. This example shows 6 of 7 typical data monitoring systems for 30 buildings, helping to overcome the challenges in comparing data from one source with another to derive insight into what's going on in the building or portfolio. Our platform offers the ability to create one data set using modern analytics to develop customizable alarms and alerts that can evolve with the buildings themselves, reflecting change of usage patterns, etc. And the data collection can be extended at any time to pick up more data as it becomes available. So if we think about the amount of data, the extent of the data that we typically have for one building, when we consider cities and communities, that amount of data grows exponentially, as does the power of the data. With Internet of Things, we anticipate and we already see more and more data becoming available. So we need very robust systems of collecting and processing that data, as well as communicating the relevant information to the various stakeholders. We've been experimenting with LoRaWAN as one example of an IoT smart sensor technology, which is one of many, but well worth a look for those that are embarking on data collection and management for building optimization. So, as mentioned, communicating the right information to different stakeholders is an important part of enabling decision making and buy-in at different levels. We can aggregate the building and network data in real time, then help the client to design and implement their own customizable dashboards or command centers, fully flexible, taking the legwork out of the capturing, processing and reporting what's happening in each building or across the portfolio or by region or by country, in fact. So I'm going to hand over to Adal now, who will talk in detail about the advanced analytics used within IES and within the ICL.
Thanks, Sarah. So today I'm going to present a bit of the work we've been doing when it comes to using data analytics to solve actually real-life problems. That includes the use of data alongside digital twins. So first, I'm going to give a bit of the starting point of this technology. The way we work in IES is that we have enabled our advanced analytics through the ability of combining different data sets, which is something that it has been described by Sarah already. So this task, it's a very important starting point. We know that data from buildings tends to be a scarce resource, so the combination of the few data sources that are available out there, it's a very, very important starting point. The second one would be the use of plots and data visualization technique, so we can observe some trends, we can predict and have an idea of how the building has been operating using historical data. We can use different type of plots, such as scatter plots or overlay, with our consultants use and determine if there is any operational problem, and they can have a say whether there is an opportunity area for having an improved energy performance. On the third part, there is other methods for data analysis, but I want to mention here that knowledge would be the third component of our advanced analytics. This knowledge only comes from building consultants, but also from actual building users, facility managers, administrators, among other actors that have a say on how the building is operating. We operate under the principle of being information rich over data rich, and knowledge becomes that key important element that guides all of the implementation of our data analytics. I'm going to spend some time just describing just small differences about all these words of machine learning and artificial intelligence that we hear all out there every day. These terms are used almost interchangeably, but there are some differences among them. So the term artificial intelligence is very general. It covers a broad range of applications and refers to systems that have some level of reasoning and they can adapt. The term was coined in 1956, but to be completely honest with you, there was never a strict definition of what actually AI means. Then we have machine learning, which are this group of efficient algorithms where the rules and relationships between our input data and our output data are learned by providing samples. So these algorithms learn from the provided data, and they are as good as the data that they have been exposed to. In the third example, we have deep learning, which is a subset of machine learning, which is what industry usually refers when they say that they are implementing AI. Deep learning tends to exploit recent computational improvements and algorithms efficiency, so they tend to provide better performance than typical machine learning algorithms, and they are typically used in applications that involve sound and video. To give an example of how these two machine learning and deep learning are implemented, we can think of machine learning as those algorithms used to create time series prediction, to predict any numerical value, to do some clustering activities, say to divide a population by typical characteristics, and regression algorithms, which are the most commonly used. Well, there are other type of tasks, but I just want to mention this. So they have an unlimited number of applications in areas like finance, risk assessment, retail, marketing, and more recently in the built environment. Deep learning is commonly used, for example, in natural language applications. So everybody knows the Hey Siri thing, that is basically a deep learning algorithm that recognizes words over sounds, and computer vision, which is like if your phone camera can unblock your phone just using your face. That's an example of computer vision. So here's another example where we use computer vision to detect the position of windows in our building, and we prevent them from leaving them open when it's not necessary over the weekend. And yeah, in general, it's not very relevant to distinguish between AI, machine learning, or deep learning when solving a problem. We are actually more interested on solving the actual problem, and in real life, it involves a combination of techniques that enables to get a task done in the most efficient way as possible. Let's go down to the examples. So here we have used some of the previously mentioned analytic techniques to solve a problem related to the data in buildings. In this case, the lack of data in buildings. So data gaps is a typical problem faced when dealing with data from buildings. And well, fortunately, with the rise of technologies such as IoT and cloud storage, we hope to see less and less this type of issues. But in the meantime, when data gaps are present, it is possible to take advantage of historical trends during weekdays, say, and weekends, as well to take into account the correlation with any other independent variables, say, for example, the outdoor air temperature, to create what we call an interpolation model. So in this example, we can see data from fan power from a building, and there are some data present for some days. So what we have used here is some weekly trends and the outdoor temperature that we use to train a model, and then we can use this information to fill the missing data for the days where the data logging system was not functioning. For some cases, if there is a strong correlation with a known variable, it is possible to carry out interpolations over weeks or even months. In the example at the top, an unconditioned room was found to have a very strong correlation with outdoor temperature. Then it was possible to interpolate across 3 months of data. A second example is the same project that has a boiler system. So we have the same 3 months of data gaps, and we were told that the number of operating hours had remained constant, and we can see that the cooling rate of the water in the boiler had a high correlation with the outdoor conditions. Hence, we just gave a try to our analytics, and we managed to interpolate these values, and the data was later useful for further performance and analysis scenario simulation. Another important, presently more and more important application of analytics in data is when you have more and more sensors added to central databases. It is very easy, and this is from experience here, to get lost between projects. especially when each of the buildings has systems that are set up differently by various people from various fields and different sensors that they can be the same one, they are just named differently. So this issue tends to be unique for building industry due to the large number of people involved in the operation of a building. And the solution that we have seen in the recent years is the use of semantic tagging. We're going to speak a bit more about this. But here, I want to show you real examples of how the same type of sensor has been named in 3 different projects. These are real-life examples. And yeah, most of the time, this name comes from the original BMS endpoint, and sometimes it's complemented with additional information unique to the system. So we can see it's called ACMB Chiller 3CDWS, CH03, and so on. So these examples refer to the same point. So the idea is that we should create or to use a standard across projects so all the projects can speak the same language. An example of a tagging standard is it's called Project Case Tag. And just to give you an idea of how this looks, in this on the right hand side we can see how that sensor is named under that mentioned standard. So you can see that it says like cooling, living, sensor, temperature, HVAC, and then it has an ID, equipment reference, site reference, the units, and so on. So any person that is familiar with that semantic tagging, which in this case it's called Project Case Tag, will know immediately what kind of sensor we're talking about. So we are taking that direction. We are trying to unify all our vocabulary across projects, and we know that this process becomes time-consuming. Here in IES, we have developed and we are pushing the development of a process that makes this tagging quickly, and it uses a technique which is called bag of words that reads the original name and it deducts what's the information there, and then it creates the correct tagging with the correct vocabulary. So it's an example of a channel called total biomass that has been tagged by this algorithm. And we have another example of total electricity channel, which is the electricity meter from the mains, and this is how the same channel looks once it has been properly tagged. So now let's move on to another type of problems that we are facing and how we have solved them. So we have this new dilemma of the advanced versus the traditional analytics. Traditional analytics consists on expert consultants that they carry out building audits, they get data from buildings, they analyze it, and they find usually energy inefficiencies as well as energy saving opportunities. So it's all good up to this point, and we still rely heavily on our expertise to get to this point. But the problem is that during the following data inspection, say the same review period, say from 6 months to 2 or 3 years, the engineer tends to notice that some issues where they occurred at some point between that period, but they were never addressed. So the intention of using advanced analytics is to complement the traditional analytics process so we can keep track of performance of all those problems found, and then we can fix them as soon as they appear. In the following slides, I will present some plots that are just screenshots of live advanced analytics projects, and I want to mention that here another characteristic of the advanced analytics is that they have been carefully made in order to be deployed efficiently and to scale well, so we can create all these analytics in any number of sensors, from dozens to hundreds of or thousands of sensors without a heavy computational load. And that's part of the journey that we are exploring here in IES. So let's start by anomaly detection, which is a dynamic process where new data values from your sensor are compared every time to an expected range of values. So we can determine whether that new value is normal or expected, or there is some anomaly. So that expected range is generated from data trends, and in this case we're using machine learning algorithms. So this value can include many independent variables, such as trends from the recent past weeks, also outdoor air temperature, holidays, calendar, weekend patterns, and so on. So once we receive a new value and we notice that it falls outside those bounds, we can determine if this value is actually an anomaly or not. In this example, we can see a plot of the indoor air temperature of a room, and we can see that as the value falls outside that bound, there is an orange sign saying that there is an anomaly, because that value is not only outside the bounds, but it's going away from that value. And once the anomaly is corrected, you can see that the value stops being an anomaly as it seems to head back to the expected range. So anomaly detection becomes relevant for large number of sensors in the range of thousands. So facility managers, they are enabled to have an idea of where to start looking for faults and other operational anomalies efficiently. So this might not seem very interesting if you have just one channel or two, but if you have thousands of sensors, this is your best friend. For operational drift. So this is defined as the loss of performance over time after a handover or after a recommissioning effort. So we can use some predictive analytics that will enable to make direct comparison of how the building is performing with respect to the last year. And we can see here a couple of examples. On the left-hand side, we see time series electricity readings, and then compared to the trends of electricity use for the year 2018. And then we can see if those values tend to be higher or lower as the expected range. So that enables you to take action if your building is starting to drift in terms of efficiency and energy consumption. The same example, but in terms of aggregated demand, can be used for heating energy, where we can see the monthly heating demand as compared to the previous year's trend. For energy use and generation, we can use predictive models to have an idea of the next day energy use, taking advantage of weather forecasts. So additionally, predictive models can be deployed to monitor the current versus the expected energy generation of photovoltaic panels and identify quickly if there is a performance issue or any data anomaly. So here we have some examples of time series data prediction using a 24-hour forecast, and on the right-hand side we see a weekly energy generation, both from a model and the actual date. So at the end of the day, the use of this type of analytics have the intention of keeping the internal conditions of a building within acceptable comfort levels, but also avoid energy waste. For instance, preventing the heating to be left on during a weekend and other more complicated things. So we also want to closely monitor systems and keep track of their performance in order to be able to predict system degradation or malfunctioning before it happens. Comfort and system failure prevention are expected to reduce costly downtime in system as well as occupant complaints, which is a key element of our philosophy. And in the context of measurement and verification, we are pushing actively the field of machine learning to generate reliable and accurate baseline models that can effectively be used for estimation of energy savings. The team of R&D in IES relies on building energy experts, relies on data scientists and software developers that work together towards solving real-world problems. And I'm going to hand over to Sarah now.
Okay, we're going to have poll 4. Thanks very much for that, Adele.
So we're just going to look with this poll just a bit about whether you've actually got any projects in mind that you're thinking about using some kind of digital twin technology on. So actually, quite a high percent of you have got projects that you're thinking of using this kind of technology on, just over 50%. The rest mostly no, and then some with the technology being a little bit too early.
So we want to delve into some of the case studies now, just highlighting the key benefits of digital twins and tackling community or city level energy and sustainability questions. But first, I would like to just go through the ICL technology and explain a bit, just for those that haven't come across this before, exactly what it comprises. So starting at the bottom right of this diagram, we have the VE, which is virtual environment. This is our new design and retrofit suite of tools, which has been around for 25 years this year. It is used worldwide on large projects by large design firms to assist with building compliance, investment decisions, environmental performance, many aspects of design of buildings and retrofit. Next to that, we have iScan, which is the building operation and control platform. So this is where all the operational data is collated and interrogated. Then we have IVN, which is the Intelligent Virtual Network. This is where we would analyse existing and new networks. We can add any configuration of network component, for example, PV panels, wind turbines, electrical or thermal storage batteries, electrical vehicles, and we can figure out which is the best solution. So in putting together positive energy blocks, for example, we need to be able to represent all of those components on the network alongside the buildings themselves. So ICD is the fourth component, that is Intelligent Communities Design, which takes the concept of the VE applied to individual buildings and applies the same capability to large-scale models, so district campuses, cities, communities. And all of those elements are integrated around the cloud collaboration portal, which is what we use to push the data out via dashboards and command centres. And we'll see examples of those. So we can use this collaboration cloud to create intelligent community or portfolio models, which can be shared with project teams, or indeed anyone anywhere with the appropriate access permissions. Now, all of the case studies that I'm going to go through can be found on our website. I'm not going to go through all of them in detail. The first few are really just a headline to say we use the ICL tools to tackle energy-hungry buildings. We also use them for campus planning or community planning tools, in this case looking at energy, water, comfort and PV panel performance. We can use the tech to inform, as I said, return on investment calculations for proposed buildings and network configurations to answer the big questions like how do we get to zero carbon quickly and cost effectively, whether it's a campus or a community or a school or whatever. So now I've got 4 case studies which I do want to go into in a bit more detail. The first is Limerick Lighthouse project, which is part of the Cities Exchange. IES are working with various partners with the aim of creating clusters of buildings termed positive energy blocks. We are currently in phase 1, which involves upgrade of existing building stock within an older part of the city. The project looks at energy transport, building upgrade and social development, and it's a specific example of how digital twin technology can support the shift to zero carbon communities. So the goal of this overarching project, which is a European Commission programme, Positive Energy Districts, it's one of the most ambitious visions and aims at supporting the replication of this positive energy district across Europe by 100 cities across Europe by 2025. The next phase, after the sort of upgrade of the buildings, focuses on replacing fossil fuels through installation of heat pumps, solar PV, and the use of other local renewable technologies. Then looking at integrating technologies at the building and the district level via district heating schemes, community batteries, for example, and then ultimately looking at the possibility of an energy trading platform that will allow the community to trade energy on a peer-to-peer basis. So examples of how the digital twin capabilities are being used include the community information model that helps to identify the priority requirements and sort of sketches out a complete picture of the current energy demand. We use technology to create detailed virtual models for initial building analysis. We can then aggregate that data from multiple sources, use advanced analytics, as Adal has described, to build calibrated models, and then use the virtual networks to look at the interdependencies between system, changing demand profiles, alternative energy sources, so that's all the IDN side of things, energy storage, the role of electric vehicles, and understand the potential impacts on the electricity networks. So the project's at its early stages, but it is hoped the way that the digital twin technology is utilised in this project to inform decisions and engage the wider community will be of interest to many other cities as they look to meet their climate goals. Community energy systems are not just about technical innovation though. There is a big element of the research and the work going in which is interested in the communities themselves becoming active players in their local energy system, much closer engagement with the design and operation of the systems. So behaviours and individuals' responses to the systems are as much part of that system as the technical components that enable the new approaches to production and consumption of energy. Understanding the relationship between technical innovation and community engagement is a key element in this next project, which is an ambitious regeneration project in Trent Basin in Nottingham. So this project is really interested in accelerating the adoption of community energy systems as a new approach to supplying locally generated heat and electricity to homes and commercial buildings, obviously with the ultimate goal of reducing cost and carbon. The development comprises 120 dwellings, a solar PV array, and Europe's largest community battery installation. So IES have developed the Trent Basin Community Information Model in collaboration with Nottingham Trent University. The SIM is an interactive online platform that displays historical and real-time data of the Trent Basin community, so all the dwellings and the solar array and the storage on site. The primary aim of the visualisation tool is to engage the residents, informing them of the common energy generation, storage and consumption. So they can either use the online platform or they can use this communal touchscreen, which you see on the slide. They can access community energy data to enable them to make more informed decisions and to contribute to the optimisation of the overall scheme. They can also compare their own household level data with the community average, see how much energy is being generated, how much is being sold to the grid, and look at additional real-time data such as weather in the local area. So, university campuses, as we mentioned earlier, provide a very good example of a sort of bounded problem or bounded sort of set of problems. They actually serve as a microcosm of many city challenges because of their mix of buildings, distributed population of staff and students, and specific transportation requirements. So Nanyang Technical University in Singapore has a vision to be the greenest campus in the world. The university has 40,000 students and staff, and the campus consists of 200 buildings. The university is the first to sign up to our Living Lab programme, with researchers and students creating digital twin to help achieve its goals of reducing energy, water and waste footprints by 35% by 2020. So here, the Intelligent Communities design tool was used in phase 1 to provide an overview of energy consumption across the campus building stock based on existing energy and building stock data. The resulting model enabled the quick identification of immediate energy savings, leading to 10% reduction in campus energy and a financial saving of around 4 million Singapore dollars. Phase 2 then focused in on 21 buildings in the campus for a more detailed investigation using our collect, investigate, compare and invest process, and identified a further 4.75 million Singapore dollars and 9.6 kilotons of carbon savings. So this is a good example. A good example here also arose in the implementation of the digital twin to improve decision making around the campus cooling system. The campus management team wanted to understand if decentralised cooling systems in each building would be more efficient and cost effective than a centralised multi-building system. And the campus information model enabled them to analyse alternative scenarios using time series data to show the performance of different systems, demonstrated that a centralised system provided a significant reduction through the life cycle. Another good example of how digital twin technology can help is these sort of bounded communities, is this project on Ede, which is an island in the Orkney archipelago in northeast Scotland. The community was looking to reduce its energy consumption, improve the comfort of local homes and reduce emissions. So the island is already home to a large wind power facility, but this is isolated from the island's electricity system. Many homes, however, have their own 5 kilowatt turbines installed. So initial engagement with the community highlighted their concerns as the need to make their homes more comfortable and to benefit from local energy resources, reducing their dependency on the mainland grid, which can be a bit hit and miss. So they wanted to build resilience in developing their own supply. They were very interested in becoming a zero energy community. They wanted to understand if that was economically viable. The IVN tool, so the Intelligent Virtual Network, was used to create a network model of the entire island and all of the buildings on the island, based on information from local distribution network operator and the energy profiles for the various buildings. A zero carbon scenario was then explored by adding interventions, including improving the building fabric, replacing lighting with LEDs, switching over to heat pumps, etc. And in total, 76% of energy savings were identified just by making those interventions. So there's already existing high wind resource on the island, which makes a move towards electrification of heating systems and addition of storage systems much more financially viable than for other communities. And also they proposed to put local energy storage to give them the flexibility in sort of maintenance of supply. So they, based on their analysis using the IVN technology, they selected a 500 kilowatt per hour battery as offering the best payback period for the community and the lowest upfront cost. Okay, so in summing up very quickly, digital twins offer a new approach to really take advantage of the advanced analytics, the new technologies that are finding their way into the construction domain, and really help us to tackle design, construction and operation of community scale projects. So some of the advantages that we've seen, I just want to draw them out. Understanding the data, capturing the data in one place, being able to run the analytics on it to get a real insight into what's happening in real time. Creating and maintaining this link between the real and the virtual world. So once that's established, that should survive through the sort of life cycle of these projects at the very least. The likes of the university campus, that connection will be maintained through the life cycle. Homogenisation of data, decision support through design and operation, insight and optimisation through the asset life cycle, closing the loop. So importantly, with all of these different initiatives going on, we want to be able to measure the outcome to see that the expectations have been delivered. And if they haven't, then why not? Why have they not been realised? And what can we do to improve that? The technology is evolving and, can be changed as the project objectives change. It's fully flexible and customisable and accessible. So in terms of stakeholder buy-in, when we go down to this level of positive energy blocks where we need to get buy-in from lots of different stakeholders, then they can see the real data and they can make informed decisions.
So we're going to have one final poll before we go into questions. Just having a think about the most important stage in the built environment lifecycle for using digital twin technology. And then I'll just share the results with you quickly just so you can see that one. It's quite interesting actually, a lot of people coming in on the building operation control side and then followed by master planning.
Okay, so if there's any aspect of what we've talked about, whether it's training, the technology, more in-depth demos of any aspects of any part of the software, including Nadal's advanced analytics, then please do get in touch and we'd be happy to provide that information for you. We can help you get on your digital transformation journey. Okay, I'd like to thank Adal today for his input and Ed with the polls. Brilliant, thanks very much. And from myself, I think we're going to sign off and talk to you next time. Thank you.